Hey kids, it is time for Unit 6. Imagine this drive-by that I went to a McDonald's. Wow, right? Look at what's on their sign. Can you believe that? Craziness. All right. So in your notes, in your warm-ups, make sure that you indicate that this is where Unit 6 starts. All right. Unit 6 goes even to our Unit 6. There are some topics in your book in Chapter 5 that we pull problems from. And this really is where we're done with AAF topics, right? The most of units 1 through 5 was stuff that you had done for a year in pre-cal and just went over really quickly. We are now leaving AAF. Everything that we're going to do from now on really is brand new, right? At least from the perspective of it wasn't taught in pre-cal. So fundamental identities, and we do mean trig identities from here. So your job is to be able to simplify, that's one objective, simplify trig expressions using basic identities, also evaluate trig expressions. Today we are going to focus on simplifying. So the first thing I have to make sure is that you know your identity. So there's a handout, a note sheet for this for Unit 6. Your reciprocal identities are not new. Right? You knew this. Cosecant is 1 over sine. Sine is 1 over cosecant, right? Those are your reciprocal identities. So sometimes these are useful. When I think about using these is sometimes when I'm simplifying two fractions and I might need a common denominator. These might come in handy. Or sometimes when I have maybe cotangent in my numerator and I have tangent, I might want to rewrite the tangent as 1 over cotangent in order to be able to cancel. Quotient identities, right? I don't normally call these quotient identities. I just call this tangent. But tangent is a quotient identity because tangent and cotangent are actually both ratios. Sine to cosine or cosine to sine. Sometimes I actually need the fractions as opposed to having tangent. Hey, why don't you divide sine by tangent? Just 'cause. Math jokes. Pythagorean identities. This is your unit circle, right? From your unit circle, we drew triangles in AAF. We drew triangles in here. For instance, at 45 or pi over 4, that's a right triangle. The x-coordinate is 1 over root 2. The y-coordinate is 1 over root 2. And when you square 1 over root 2, square 1 over root 2, add them together, take the square root, you get the hypotenuse, or as the radius of the unit circle, 1. Cosine squared plus sine squared, no matter where you are on this unit circle. Cosine squared plus sine squared will equal the radius 1 squared, which is just 1. And then these other Pythagorean identities are just rewrites of those things, right? For example, right, I can take this. Another way to think about this is, well, that's 1 plus sine squared on top of cosine squared is equal to 1 over cosine squared, right? That's another way to think of this identity. Of course, I could also think of this as cos 1 is cosine squared theta over cosine squared theta, isn't it? Plus sine squared multiply everybody by cosine squared and look what you get. The unit circle, right? I can do the same thing with this one. Cotangent squared is cosine squared over sine squared plus sine squared 1, which I can rewrite 1 a lot of different ways. Multiply through by sine squared, and you get the unit circle. Right? The unit circle is important, comes up all the time. So they also can appear in multiple different formats. Right? Notice that here I just got sine squared by itself. Get sine squared by itself by subtracting cosine from both sides. Or I can get cosine by itself. The second one, 1 plus tangent squared, I can subtract tangent squared from both sides. Or I can subtract secant squared. Right? Get tangent squared by itself, and subtract 1 from both sides, right? So each one of these is just algebra 1. Algebra 1 rewrites. So let's use some of those to simplify. Right? Let's simplify this expression. Cotangent of some angle times secant of some angle times sine of some angle. Well, let's just start messing around. How can you rewrite cotangent? What's another way you can write secant? Hey, look what happens. By, this simplifies to 1. So no matter what angle you pick, if you multiply the cotangent of that angle times the secant of that angle times the sine of that angle, you will always get 1. Crazy, right? Let's do the next one. Please, please don't tell me that sine squared plus cosine squared. It is not, right? You know how to square x plus y squared. That is x squared plus multiply and double plus y squared. So what is sine x plus cosine x all squared? Sine x is squared, but then sine x is multiplied times cosine x and doubled. Then you're going to add sine x minus cosine x all squared. So you are going to square sine x, multiply sine x and cosine x, and double, but you have a negative. And then negative cosine x times negative cosine x is positive cosine squared x. So what happens here? By sine squared x plus cosine squared x is what? That's my unit circle. Plus, oh, hey, another sine squared x plus cosine squared x. What is that? Oh, hey, and what's 1 plus 1? Snap, 2. Crazy how that works, right? What? Now remember, none of these are equations. I can't like multiply both sides by 4, right? I can't, all I can do is legally rewrite. So, what is this? Wait a second. Look at those Pythagorean identities. Do you see one that has tangent squared in it? What can you rewrite tangent squared as? What can you write that as? right? If you look at that, you can rewrite that as secant squared theta minus 1. That's darn close to that numerator, isn't it? Hey, hold on a second. Let me ask you a question. What happens from algebra 1 when I asked you to factor x squared minus y squared? How do you factor that? Since that is the difference of two perfect squares, isn't that x plus y times x minus y? There is a reason you should have done that 500 times in algebra 1. I see x squared minus y squared here. Do you? Secant theta is squared minus 1, which is squared. This is the difference of two perfect squares. And how do you factor the difference of two perfect squares? Secant theta plus 1 times secant theta minus 1. And that's all on top of secant theta plus 1. What happens now? By you are left with secant theta minus 1 minus secant theta plus 4. What happens? By negative 1 and 4? 3. See what I did there? 1, 2, 3. Snap. Yes, I chose those on purpose. All right, let's do some more identities. Use the basic identities. So that's what you have your note sheet. Your note sheet is your basic identities. Use basic identities to find sine theta and cosine theta. So there's two things I want to find. If tangent theta is 5 and cosine theta is positive. Now, I don't need basic identities to do this, right? If tangent theta is 5 over 1, I have a triangle. Here's theta. Tangent is the opposite over the adjacent. What's the hypotenuse then? 1 squared plus 5 squared, which is 26. Sine theta then is 5 over 26, root 26. And cosine theta is 1 over root 26. No, I do not need to rationalize that. I've answered the question, but I didn't use basic identities to answer it. So in this unit, if with these directions, you would get answer points, but you would not get rubric points for the work. So let's see how they want us to do it. When they're asking us to practice using our basic identities. So let me start with tangent theta is equal to 5. Now, I could rewrite that as sine theta over cosine theta is equal to 5, but I don't know where that would get me. I can't see that that would do anything for me. But I want to do something. Now, I'm not saying that you would normally think of this. This is now something I'm showing you, and now you might think of it. I do have an equation. Can't I square both sides of an equation? So isn't it true that tangent squared theta is equal to 25, given that tangent theta is equal to 5? I just squared both sides of an equation. That's legal. Now, I want you to remember the identity that has tangent squared in it. The Pythagorean identity that has tangent squared in it is 1 plus tangent squared theta is equal to secant squared theta, isn't it? But tangent squared theta for us is equal to what? Oh, snap. with the information that we were given, we know that tangent theta is 5, so tangent squared theta must be 25. Therefore, 26 must be equal to secant squared theta, taking the square root of both sides. Secant theta must be equal to 1 over root 26, because it's really over the square root of 1 over 26, but the square root of 1 is just 1. Now that's really plus or minus, but remember, secant is the reciprocal friend of cosine, and cosine, they told us from the beginning cosine was positive, so I don't need the negative. Oh, sorry, I was ahead of myself. Secant is plus and minus the square root of 26. But again, because cosine is positive, cosine of theta, I only need the positive, is 1 over root 26. Check. So now go up here, and again, I could still go to my triangle, but using basic identities, if tangent theta is equal to 5, that means I now will use the quotient identity. Sine theta over cosine theta is equal to 5. But I just found what cosine theta is equal to. So I'm going to write sine theta divided by 1 over root 26 is equal to 5. Get sine theta by itself. Right? Multiply both sides by 1 over root 26. So I knew those answers without basic identities. This is one of the things, if you have tangent equal to something, and I want to use one of my basic identities, I tried the quotient one first, but it didn't, right? I tried just thinking about, well, I tried doing this identity first, but it didn't get me anywhere. So I said, what other identity do I have that has tangent in it? Oh, I don't, but I have tangent squared. Oh, okay, well, I just, right? So that's the kind of thinking process I use. A lot of these things is trial and error. So next on your note sheet is cofunction identities. I've never called them cofunction, but you've seen these before. They're the shifts, right? So if I have cosine, I could rewrite it as sine, right? We've done this before. So that's not new. Odd and even identities, right? This comes from your definition of even and odd functions. Sine is an odd function. So is its reciprocal friend. Cosine is an even function, right? Think about sine. An odd function graphically has point symmetry around the origin. An even function has symmetry around the y-axis. What's tangent then? You can already tell, right? But tangent certainly has symmetry around the origin. And the reciprocal friends are the same. So here's an example from your textbook. If I am told that the cotangent of the opposite of some angle is approximated to be 7.089, and they ask me to find tangent of negative pi over 2, look at your cofunction identities. Do you see one that relates tangent and cotangent? Yes. So are these the same? Well, I'm not sure, right? Because what I have is the tangent of not theta minus pi over 2, but pi over 2 minus theta is my cofunction identity. And it's equal to cotangent of theta. So what can I do to legally rewrite myself into the identity I want to be able to use this identity. Factor a negative out of here. Factor a negative out, and I get theta minus pi over 2. Now, staying on this side of the equal sign, now look at your even odd identities. Tangent of negative something is the same as what? Crazy. Now, what is cotangent? Cotangent of theta. I don't want cotangent of theta, though. I want cotangent of negative theta because I have a number for that. Look again at your even odd identities. Cotangent of theta I want cotangent of negative theta. How do I get that? Well, let me not even do that. I'm sorry. Let's do this. Let's just bring this straight down. I haven't done anything to it. Now I have an equation. I was asked to find positive tangent of this. How about I take this negative and move it over here? Right? Divide both sides by -1 or multiply both sides by -1. But look at the even odd. What is true about negative cotangent of theta? What is that equal to? And wait a second, don't we have a number for this? I feel so fancy and accomplished when I'm done with something like this. So I say QED, which is Latin for errata dictum or something like that. I don't know. But it basically means, so let it be written, so let it be done. Right? It basically means, and I'm done. And I'm out. Basically, this means mic drop. That's what this means. QED means mic drop. All right, let's do another one. Simplify. That is just a period there. I just felt like it's a sentence. I should put a period after it, but then it looks weird after a fraction. Oh well. Simplify. Again, here is a strategy that I am used to using because I've done a lot of these. In this case, I don't have an equation. I can't like square the numerator and square the denominator or divide the top and bottom. But the only thing I can do is multiply or divide by 1. That's all I can do. I'm telling you to multiply by 1. But I'm going to be very clever about my 1. I chose, of all the ones in the world, I chose that one. Now look at my numerator. I didn't know what to do with this, right? I didn't know what to do. I certainly can write that as 1 plus sine over cosine, and this is 1 plus cosine over sine, and maybe I could do something with that. And I'm not saying that you couldn't eventually get where you need to go. However, this was an efficient thing to do, and this is a really nice trick to have in your bag. Multiply by convenient ones. So look what happens when I do that. Distribute, right? And I get a tangent squared. I have a tangent x plus tangent squared of x over tangent x. Don't you dare cancel those tangent x's. It's not a factor, it's a term. But look what happens here. Cotangent x times tangent. What is that? These are reciprocal, friends. What happens when you multiply reciprocals? Cotangent is 1 over 10. Tangent. 1 over tangent times tangent is what? Look at what I did to the numerator. Factor. And look at what the denominator is. Oh, snap! What happens? By, and I have simplified that fraction to just tangent of x. Mic drop. Now, in reality, I'm being a little ridiculous here. In reality, this is stereotypically used when I'm done with proofs, but trig proofs is where we're going. Simplifying trig expressions is critical to be able to do trig proofs. All right, let's do this one. Simplify. So again, something I picked problems in particular to show you for a skill or a trick that I want you to make sure you've got in your bag. So when I see two fractions and I'm trying to simplify, that's like giving me 3/5 minus 4/7. Simplify that. That means get me one fraction. That means get a common denominator. You need to get a common denominator. What's the common denominator between 5 and 7? Isn't it 35? The product of them two. So guess what the common denominator is between secant x minus 1 and secant x plus 1? Right? Now, what would you multiply 5 by if you're to get your common denominator? So I've got to multiply top and bottom by secant x plus 1. Secant x plus 1 times secant x plus 1 minus, what happens here? I have to multiply, right, just like you would have to multiply by 5 and multiply this by 5. Multiply the numerator times what's missing. Multiply 1 by secant x minus 1. Simplify this numerator, secant x minus secant x, by, be careful, this is 1 minus negative 1, which is 2, over secant squared x minus 1. X minus y times x plus y. That's the difference of two perfect squares factored out. Put it back together. Why would I want to do that? Because there's a Pythagorean identity. If you can write a fraction as not a fraction, you are expected to. Woot, woot. That was no more complicated than doing this. Right? It's the same thought process. Fractions. All right, we will do more when we are together in our live session, but that was your first exposure to simplifying trig expressions using basic identities. Congratulations.